Hi there. I'm making a video about group theory because I find it really fascinating. It's a theory about symmetry in molecules, which is really important for bonding and infrared spectroscopy. So I barely have a grasp on it myself, but I think that teaching people is the best way of learning. So group theory is going to rely a lot on like basic concepts in chemistry. So for this episode, which is going to go over symmetry operations, you're going to need a pretty decent grasp on VSEPR theory, which, if you remember, is the theory that lets you determine a molecule's shape based on the number of atoms and lone pairs around the central atom. So symmetry operations are operations we do on a molecule where it looks the same after the operation is done. And this will make more sense when we actually do them. The first symmetry operation is the identity operation, which we give the symbol E. And that's the most simple one. We just do nothing to a molecule. So I've got methane here, which is tetrahedral. If we do nothing to this molecule, it looks identical. So this has the E operation, and that's true for all molecules that exist. That's the identity operator. The next one is the inversion, which we give the letter I. That is where you take a point and pass it through the center to get to the other side, like the equidistant from the center. So for example, on this octahedral molecule, maybe this is sulfur hexafluoride. This is the center of the molecule, the center of symmetry. If we pass this fluoride through the center and to the other side the equal distance, it encounters another fluoride, which means that it looks identical when you invert it. And I'll take a different example, one where it doesn't work. In methane, this is the center of symmetry, the carbon here. If you pass this point through the center of symmetry and to the other side, there's nothing there, so it doesn't look identical under inversion. So this doesn't have the inversion operation in it. The next one is rotation, which we give the symbol C and subscript N. And that is rotating a molecule around an axis by 360 over n degrees. So here's an example of water. It's what we might call bent. You can see that if we rotate this molecule 180 degrees, this hydrogen has gone to this hydrogen. It looks the same. And that was around this axis, coming down through in between the hydrogens, through the oxygen. And we rotated it by 180 degrees, which means that was 360 divided by 2, n equals 2. So that's a C2 operation. There's actually only one on this molecule. But let's look at a trigonal planar molecule, like maybe this is borane, maybe. You can see that this is the center of symmetry here. If we put a principal axis, just an axis, through this molecule, like going into me, and we rotate it by 120 degrees, it looks the same. This hydrogen has gone to this hydrogen has gone to this hydrogen, and this hydrogen has gone to this hydrogen. It's identical. And since that was 120 degrees, which is 360 divided by 3, this is a C3 rotation. So yeah, this has C3, and you may notice that if we were to put an axis through this bond here that goes through the hydrogen and the boron, we could rotate it 120 degrees, and it would look 180 degrees, and it would look identical. So there's a C2 axis on each one of these, through each one of these bonds. Basically, for a molecule, the axis with the highest n value is the most important one. So in this case, the C3 axis is more important than the C2, and we call the most important one the principal axis. That'll become more important later, but right now, don't worry about it. Let's go over this one. This has, you might be able to tell that if we put an axis through that atom, we could rotate it any number of degrees, and it still looks identical, right? That's what we call a C infinity axis, because we can divide 360 by an infinite number of rotations, and it still looks identical the whole way through. So that's C infinity. So that applies to all linear molecules. Next one is reflections, which we give the symbol sigma. For that operation, we move through a plane, a reflection plane, equidistant the other side, and if it looks identical, then it has the reflection operation. Let's go over water again. Let's put a reflection plane through the oxygen into U. So it goes through into the plane of the camera. And then we reflect the molecule. So this hydrogen goes through the plane and to the other side, and it encounters another hydrogen. Sorry. That means it looks identical after a reflection through this plane. Sigma V is a reflection plane that goes through the principal axis of the molecule. It contains the principal axis. So this principal axis of water is the C2 here, where we rotate it and it looks identical. So the reflection plane contains that rotation axis, and so we call it a sigma V for vertical, obviously. So the principal axis in the linear molecule is this C infinity through here, through this bond. And so a reflection plane doesn't work on this one. Give me a second. Here it is. Here's my revised molecule. See, now they're both the same. Sorry. So the reflection plane that goes through the center of symmetry in between these two bonds, in between these two atoms, that reflection is perpendicular to the principal axis, and we call that a sigma H. As you can see, the reflection is true, because if you reflect this atom to this atom, it looks identical. Improper rotation is the final one. So we will look at methane. What happens if we look at it from this angle and we rotate this by 360 divided by 4, 90 degrees, and then we reflect it through a plane perpendicular to that axis that we just rotated around. it looks the same. That might not be obvious, but that is an S4 for being the degree of rotation we went around. There's an S4 operation, an improper rotation. Let's do it again. So you can see the hydrogens pointing towards you are going up and down. We'll rotate it 90 degrees. Now they point left and right? And then if we flip it through this reflection plane, in the plane of the camera, that's like through here, right? If we flip it through that, I mean, I'm rotating it, but it's flipping it. It looks the same, right? Up and down. I think you get it. You probably haven't noticed, but something that is true. Well, maybe you have, because what I just did just then, by flipping this, I did both a C2 rotation and a mirror plane, right, along here. Molecules containing one operation will often contain more than one operation, which means we can categorize molecules into groups, which we call point groups. And the way we categorize them is by using this flowchart here, which is pretty cool. We'll go through an example. So here is water. The first question on the flowchart is whether this is linear or not, which we know is not true. It's not linear because it's bent. Water isn't linear. Everyone knows this. Are there two or more Cn axes where n is greater than 2? We have one C2 axis here, and we don't have any more C2 axes, so that's so the answer is no. Is there a Cn axis at all? Yes, there is, because we just worked out this is C2 here. Does Cn, which is C2, have n C2 perpendicular to Cn? We look here. Is there a C2 axis like going into the camera? No, because if you rotate this 180 degrees, it doesn't look the same. And there's not one here either, because if you rotate this 180 degrees, it doesn't look the same. So the answer is no. Is there a sigma H? Nope, because if we flip it along perpendicular to the principal axis, it doesn't look the same. Is there a sigma V? We know this. There are n sigma V's. So 1, flip this to this, and also 2, where nothing changes, right? If it goes through the atom, then it doesn't change because we're counting them as points, right? So this means that this water atom's point group is Cn, which is 2V, so C2V. Water is in the C2V point group. Awesome. Let's do another one, which will be HCl. Here it is, HCl. Let's go through it. Is it linear? I think it might be linear. Yes, it is. Does it have an inversion center? You remember an inversion center is moving one point through the center of symmetry to the other point, equidistant from the center of symmetry. And actually, in this molecule, there is not a center of symmetry, because if we move this hydrogen, it encounters the chlorine, and if we move the chlorine, it encounters the hydrogen. That's not identical, so it would look like this, right? That's not identical. So this gets the point group C infinity V. If it did have a center of inversion, it would be D infinity H, right? Follow the flowchart. Easy. Isn't that easy? That's so easy. What's the other one? Let me just move the camera so I can actually see it. Oh, methane. Yes. Is this molecule linear? No. Does it have two or more Cn axes where n is greater than 2? Well, we can see here through this bond, there's a C3 axis, right? Whoop, whoop. And that's true for all bonds, so yes. Does it have an inversion center? We did this one earlier. No, it does not. So if we invert through the center of symmetry, it comes out to the other side, and there's nothing there. So it would essentially be like this, right? That's not identical, and therefore this point group is TD, which is tetrahedral. And we know methane is tetrahedral. That's just basic chemistry. So there we are. I hope that was useful. I would love it if anyone could tell me if I did anything wrong, if I need to update this. Yeah, thank you. Next time we'll be going over group multiplications, basis sets, and the character table. Thank you.